We're now studying differentiation. Firstly, with what we already know is a gradient of a line. And a gradient of a line is constant because it's a straight line. Therefore, the y2 minus y1 over the x2 minus x1 value is the same for any 2 points on that line. The gradient of a curve, however, is different. The gradient of the entire curve cannot be calculated, obviously, because it's a curve. And therefore, these values will be different for any 2 points that you take. Therefore, there has to be a way to calculate the gradient at a single point. Yes, like this right here, like this right here, or like this right here. The way we do it is we draw a tangent at that point. So we know what tangents are: straight lines that touches the curve at exactly one point. So if you want to find a gradient at this point right here, then what you'll have to do first is draw a tangent at that point. Then you will calculate the gradient not of the curve but of the tangent at that point to get the gradient of the curve at that point. Let us look at a deeper explanation of the way we get this gradient of a single point. Suppose there's a curve y equals to x squared, which is this curve right here, and we want to find the gradient at the point xy. Yeah, a general point xy. That xy obviously can be written as x squared because the curve is y equals to x squared. So suppose there's a point P which is written by xy, and we want to find the gradient at that point. Because we need to draw the tangent, we can lead up to the tangent. So let's just say we take another point on that same curve, we call it A, and we draw a line connecting P and A. This is definitely not a tangent, right? Because it touches at both A and P. What this is a chord. And to find the gradient of that line, you will just take the coordinates of A with the coordinates of P and find the gradient using y2 minus y1 over x2 minus x1. So let's make A to be the same x from P plus a small x, a smaller x, a very small number x. And the same thing for y plus a small x. You can name it whatever you want. I just named it delta x. Then the way we're going to do it is y2 minus y1 over x2 minus x1 right here. From this we know that y2, which is a point of A, is just the x squared, right? So we're going to write that down. X plus a small increase in x squared minus y1, which is the y value in P, which as we know is x squared. Then divide by x2 minus x1, and we're going to do the same thing right here. Expanding the bracket, we'll get x squared plus 2x delta x plus delta x squared, and then minus x squared at the end. And at the bottom, the x and the negative x will cancel each other out. We'll be left with delta x. So then we end up with this thing right here. And so as our point A comes closer and closer to P, so initially we had point A to be far. Suppose it comes closer and closer and closer. What is happening to that delta x and delta y value is that it is approaching 0 because that P, because that A is coming closer and closer to P. Therefore, their coordinates are also getting closer to each other. So this delta x is getting closer to 0. But before that, let's start off simplifying this. We have 2x delta x over delta x. I'm just splitting the fraction, plus delta x times delta x over delta x. This is delta x squared, right? We can cancel out delta x from both of them. We end up with 2x plus delta x, which is what they got here. As A comes close to P, this delta x is becoming 0. Therefore, what we're left with is going to be 2x. Now, how do we know it's a gradient of the curve at P? We have another point A, which is extremely close, so close that we have the delta x as 0. Therefore, it is basically another point at P. So we have a line connecting 2 points, one point being P and the other one being so close to P that it is practically P. Therefore, that line touches the curve once at P. And we can find the gradient of that line, and that gradient was 2x. Obviously dependent on what that x is. And that is how we find the gradient of a curve at a certain point. This method is known as differentiation. So in general, if you have a y equals to ax power n, which is a general form of a polynomial, then its differentiation will be a times the power n and then x power n minus 1. Okay, and obviously this can be translated to functions as well, where there's a function and its derivative, where if the function is equal to ax power n, then the derivative is a times the power, then x power the original power n minus 1. And we can see with a few examples here. Differentiate the following and find the gradient when x is equal to 2. Remember, as we just said, the derivative is the gradient of the tangent at the specific x value that you choose. So let's just start off with this. To get the derivative dy over dx, we get 6, the number that's there already, the coefficient, times the power, the original power, so 5, then x power 5 minus 1, so 4. Same thing for this. We take our coefficient 5 times negative 2, the original power, x power negative 2 minus 1, which is negative 3. Then 4 over x is just 4x power negative 1, where again, we're going to take the coefficient 4 times negative 1, x power negative 1 minus 1, which is negative 2. For this is just x power a half, which again doesn't have a coefficient, so we'll just multiply a half times x power a half minus 1, which is negative a half. Then y equals to 5. 5 is just 5x power 0, and therefore we'll have 5 times 0 x power 0 minus 1, which is negative 1. And obviously this is going to end up becoming 0 because you're multiplying it by 0. This one will end up becoming 1 over 2 root x, because this x power negative a half goes down to x power a half. This one becomes negative 4 over x squared. This one becomes negative 10 over x cubed. And this finally becomes 30 x power 4. Then to find the gradient when x equals 2, you just substitute that value into the x for each derivative. 30 times 2 power 4 is just going to be 480. Negative 10 over 2 power 3, which is 8, is just going to be negative 1.25. Negative 4 over 2 power 2, which is 4, is just going to be negative 1. 1 over 2 root 2 is just going to be root 2 over 4. And 0, meaning it's just going to remain as 0, because whatever x you put, it will remain 0. You can't even put an x into this. Therefore, these are going to be the gradients when x is equal to 2 for each of these equations. Next, we're told to differentiate this expression right here with respect to x. So what we'll do here is just differentiate each term. Then obviously, according to the sign, we will show it in that way. So 3x power 4, we just take the 4 to the back, so 3 times 4, x power 4 minus 1, which is 3. Then 1 over 2x squared, which is just 1 over 2x power negative 2. And differentiating this will give us 1 over 2 times negative 2 x power negative 3, negative 2 minus 1. Then this one right here is going to be 4x power negative a half. And to differentiate this, we will take 4 times negative a half x power negative a half minus 1. And finally, to differentiate 5, remember 5 is just 5x power 0. And so we'll have 5 times 0 times x power negative 1, which is just going to be 0. So our derivative will look like 12x cubed minus 1 over x power 3 minus 2 over x power 3 over 2 plus 0. So this right here will be our derivative of this expression with respect to x. Next, find the gradient of the tangent to the curve y equals to x times 2x minus 1 times x plus 3 at this point right here. So firstly, what we're going to do is expand this so that we have something that we're more familiar with. Expanding this will give us x to x squared minus x plus 6x minus 3. This right here is just going to be 5x. Then we can expand this further. 2x cubed plus 5x squared minus 3x. Differentiating this will give us 6x squared. This will give us 10x, and this will give us negative 3. Therefore, this right here will be our derivative dy over dx. Then to find the gradient at this point, obviously this point we know is x equals 1 and y equals 4. What we can do is just take our x and put it into our differential equation to get 6 times 1 squared plus 10 times 1 minus 3, which is just going to be 13. The next example, the curve y equals to ax power 4 plus bx squared plus x has gradient 3 when x equals to 1 and gradient negative 51 when x equals to negative 2. Find the value of a and find the value of b. So for that, firstly we need to find the equation that gives us the gradient, and you get that by differentiating this entire equation. Differentiating this entire equation. So we'll start off with ax power 4. Remember, you take the power down. So 4 times a times x power 3 plus 2 times b times x power 1 plus, if we have x power 1, then that 1 goes behind. We have 1 times x power 0, which is just 1. So we end up having 4ax power 3 plus 2bx plus 1. When x equals to 1, this value will be 3. Therefore, 4a plus 2b plus 1 will equal to 3, which gives us that 4a plus 2b is equal to 2. On the other hand, the gradient is negative 51 when x is negative 2. So 4a times negative 2 cubed plus 2b times negative 2 plus 1 will equal to negative 51. This gives us negative 32a minus 4b is equal to negative 52. So we have two equations here. We can solve it simultaneously. And after solving, we get that the value of a is going to be 2 and the value of b is going to be negative 3. Next, when differentiating composite functions, we will do something known as u substitution. Okay? And what this is that we know how to differentiate 2x plus 3. And we know how to differentiate if you have a u power 3. But when those things are combined, then it gets a bit harder. So what we will do is just reduce it to that u power 3. So let u equals 2x plus 3. And here our differentiation will be written du over dx. Because when the equation is y equals to something, we have dy over dx. So the dependent variable on the top and the independent variable at the bottom. Now we don't have a y, we have a u instead. Therefore, we'll have our dependent variable, which is u, at the top and the independent variable x at the bottom. Then that will equal to, so we take the derivative of this, and that is just going to be 2, which is the derivative of 2x. The derivative of 3 is just going to be 0. On the other hand, we have that y is equal to u cubed. And this, the derivative of this will be written as dy over du, because y is the dependent variable and u is the independent variable. And that will just be 3u squared. But what we wanted was dy over dx. But we got dy over du and du over dx. So what can we do here is we can multiply the two. So we can take dy over du multiplied by du over dx. What will happen here is that the du at the top and the du at the bottom will cancel. we will end up with dy over dx. Therefore, we just have to multiply these two things. So we'll take 3u squared multiplied by 2, which is going to be 6u squared. But remember, our u is this right here. So we're just going to get 6 times 2x plus 3 power 2. A way of doing this quickly without going through this entire thing, this by the way is called the chain rule, okay, is if you have something like this, where you have a bracket and inside that bracket there is a function and there is something happening to that entire bracket. Then what you will do is take the derivative of the things inside the bracket. The derivative of what is inside the bracket is just 2, because 2x derivative is 2 and 3 derivative is 0, so it's going to be 2. Then you take that derivative of the inside of the bracket, take it outside 2, then do the same thing you would do normally. So take 3 to the front, multiply by 3. Then you have your same 2x plus 3 inside the bracket, and the power will reduce by 1, so it will become squared. That will give you 6, 2x plus 3 squared. So for a general rule, if you have something like this, a bx plus c power n, this will become a times b, the derivative inside the bracket, times n, the power. Then you just have your bracket as it is, bx plus c, power reduces by 1, so n minus 1. This is more explanation on this so-called chain rule, where there is an option of still finding the differentiation of these type of equations when you can just open up the brackets, right? So you can expand this. However, you might make mistakes because there is a middle step and it's also very long. The much more efficient method is what I just showed you, which is known as the chain rule. So what you do here is you take the thing inside the bracket and convert it into a variable where you are substituting it, just like we did in the first lesson, the quadratics lesson, where we were talking about harder quadratics. So here we can introduce a variable where u will equal to 5x plus 3, whatever is inside the bracket. And therefore we'll have now two equations. One is this one right here. And we have the other equation, which is y equals to u power 7, which is the 5x plus 3, that's the u, power 7, which was the original equation. Then y has changed to a function in terms of u. And we also have a function u, which is in terms of x. Then to derive, we will just multiply the two so that this du and this du cancels out. We remain with dy over dx. So we'll derive this and then multiply it by the derivative of this right here to get our final answer that we want. Obviously, after then changing back into x terms. This is an example we have where y equals to 3x power 5 plus 7x. And what we can do is take whatever is inside the brackets and convert that into u. So u will equal to 3x power 5 plus 7x. And then we have our second equation, which is y equals to u power 4. And we are going to derive both of them. So the first one is just going to be du over dx, because u is what the function is. And that is going to equal to 5 times 3, which is 15, x power 4 plus 7. And the same thing we can do for y equals to u power 4, dy over du. In this case will be 4u power 3. Then what we will do is just multiply the two together. And we end up getting 4u cubed multiplied by 15x power 4 plus 7. That will just be 60u cubed x power 4 plus 28u cubed. Then obviously we change the u back into x. So this right here is our dy over dx, right? So we need to convert it back into x. So our u is just 3x power 5 plus 7x. So 60 times 3x power 5 plus 7x multiplied by x power 4 plus 28, 3x power 5 plus 7x cubed. And this is cubed as well. And therefore this right here would be our dy over dx. The other method that I showed you that you skip the middle steps is take the derivative of whatever is inside. The derivative of whatever is inside is 15x power 4 plus 7. Derivative of 3x power 5 is 15x power 4. Derivative of 7x is 7. Then multiply it with that bracket, 3x power 5 plus 7x, and power it by 4 minus 1, so 3. That's going to be your answer. Obviously, this being in brackets. You're multiplying the entire derivative of whatever is inside with the bracket power n minus 1. Then we can do this right here. And this looks like a fraction, but what we can do is just bring it up, and using the power laws, we can change the power to a negative. This will become 2, 3x squared plus 1 power negative 5. And then we can do the exact same thing. So convert this into u. Therefore, we have u equals to 3x squared plus 1. And secondly, we have that y is equal to 2u power negative 5. Taking the derivative here, du over dx is just going to be 6x. Taking the derivative here, dy over du is going to be negative 10 u power negative 6, which is just negative 10 over u power 6. Then what we will do is multiply these two to get our dy over dx. So our dy over dx is going to be negative 10 over u power 6, where u is 3x squared plus 1. So we're going to divide by 3x squared plus 1 power 6. Then that's multiplied by 6x. And that ends up giving us negative 60x over 3x squared plus 1 power 6. That's going to be our derivative for this equation right here. Next, we have the final example, and that is to differentiate this using the chain rule. This is a question from the past paper. So the curve y equals to square root of ax plus b passes through the point 12 and 4 and has a gradient of 1 over 4 at this point. Find the value of a and the value of b. So for that, firstly, we can rewrite this, where y is equal to ax plus b power a half. Then what we can do is treat this as u. So we have u equals to ax plus b, which is our first equation, and we have y equals to u power a half, which is our second equation. From this first equation, if you differentiate in terms of x, so du over dx will equal to a, from just this right here. Differentiation, the derivative of b is just going to be 0. Then if you differentiate y with respect to u, so dy over du, we're going to get half u power negative a half, which is just 1 over 2 root u. So after multiplying the two to get our dy over dx, we will get a over 2 root u, which is just ax plus b. So root of ax plus b. And the gradient when x is equal to 12 is going to be 1 over 4. But what else do we know is that when x is 4, when x is 12, y is 4. So we can use this equation to satisfy this coordinate right here. So 4 is equal to the square root of a times 12 plus b. And also we have that 1 over 4 is equal to a over 2 root a times 12 plus b. What we can do here to remove the square roots is just square on this side, because we want to solve by substitution. This is a simultaneous equation. Therefore, we'll get 16 equals to 12a plus b. Make b the subject, we get 16 minus 12a is equal to b. Take that and substitute it into the place of b, and we will get that 1 over 4 is equal to a over 2 root 12a plus 16 minus 12a. The 12a and the negative 12a will cancel each other out. We have a over 2 root 16, which is just a over 2 times 4, which is 8. So a over 8 is equal to 1 over 4. With that, we get that a is equal to 2. So a is equal to 2. Therefore, b will be 16 minus 12 times 2, so 16 minus 24, which will give us b to be negative 8. So a equals to 2 and b equals to negative 8. Those are going to be the values of a and the values of b.